Okay, we wait 1 minute. Yeah, guys, very good morning. Are you able to see my screen, PPT?
Yes, sir.
Yes, sir.
Okay. I think in the last class we discussed up to this. Now, just in the flexible coupling topic we discussed in the last class. So we complete this, then we go to the today our gear topic. Next chapter, gear topic. Okay, gear design. Okay. That's what my plan today. So now see here. Just to recap, this also we discussed in the last class. First couple of minutes we discussed this, then we go for the further design concept and corresponding problem we discussed today. Then we move to the gear topic. Now see here, this is the uh, flexible flange coupling. I mean, whatever we discussed, the rigid coupling, it's a clamp coupling and sleeve and muff coupling and flange coupling. These are under, sleeve coupling, clamp coupling, and rigid type flange coupling. These are under the rigid type coupling. Now this is, modified version of the flange coupling. This is flexible coupling. But what are the components? Very important while designing the flexible coupling. The bush, pin, and the lining, brass lining. These are the important components while designing the flexible flange coupling. Now, see, this type of coupling we can use for lateral alignment, we can use for axial alignment, we can use for angular misalignment, lateral misalignment, axial misalignment, and angular misalignment. I mean, wherever some suppose, as I told you in the early last class, wherever the manufacturing error in the output and input shaft, during that place we can use And wherever that two shafts are, naturally when the mechanism transmitting the shaft from input to shaft to output shaft naturally having some misalignment, either lateral or angular or axial, during the place we can use this type of coupling. But this type of coupling also absorbed the vibration and shock. But rigid coupling, it cannot be observed. Okay, now this is the applications. That's what we are using this flexible coupling. And here, this is the empirical relations we are using for designing the coupling, for this determining the dimensions of the coupling. These empirical relations we have been obtained from the design data book. Okay. Now this is the diameter of the hub. DH. It is equal to 2d. Small d is nothing but diameter of the shaft, right? And the length of the hub, or also called length of the key, is nothing but 1.5 times of diameter. And pitch circle diameter, where is the pitch circle diameter here? This is the pitch circle diameter. It's d. It's nothing but 3d to 4d, 4 times of diameter. Now this is the thickness of the flange, output thickness of the flange T. Okay. Now this is the T1. Thickness of the protective rim. Nothing but the 0.25d. Thickness of the output flange is 0.5d. Now diameter of the pin. This is a new terminology we are using in this flexible coupling. This is the diameter of the fin. Diameter of the fin here, right? This is the 0.5 times the diameter holes divided by whole square root of n. Okay, now this n is nothing but number of fins used. Here, how many fins used in this coupling? 2, 4, 6 fins are used. Okay, now we come to the further design things we are going to discuss now. See the other dimensions of the flange, outer diameter, thickness of the input flange are going to be calculated after deciding the dimensions of the rubber bush. Okay, now how the power is transmitted in this coupling? See, the power is transmitted due to the shear resistance of the fins. I highlighted because the power is transmitted. The power is transmitted due to the shear resistance of the fins. Very important. Each coupling is having different concept for the power transmission. Some couplings we used only keys, right? When used keys, only crushing and shear stress will be based on the crushing and shear resistance of the key. The power is transmitted from input to shaft to key to sleeve or hub, then sleeve to again key to output shaft, like that. Okay, here power transmitted by the shear resistance of the fins. Okay, see the flange. The input to flange, the flange of the input to shaft rotates, it exerts a force P. When the input shaft rotates, this input to shaft rotates, then this is exerting the force P on the fin. Sorry, on the bush. The force P exerts on the bush P. Okay, this is very important terminology. The force P is exerting force. This is based on this force we are going to find out the resisting force. That resisting force we are going to directly equate the amount of torque transmitted for maintaining the mechanical system in equilibrium condition. Okay, now see here. That's it. See how many bushes we are using in this coupling. 6 bushes, right? Now this bush projected area of the bush. See here now. When the shaft rotates, it take first I'm starting from this coupling. This bush. The force is acting here. Force P. Whatever the force P is acting in the, for example, this is a bush 1. The opposite bush is here. Obviously, the force should be acting this direction for maintaining the mechanical equilibrium condition. Similarly, when you are considering this bush, the force acting this direction, then here the force acting opposite direction. Hence, the I mean, this is 3, this is 4, this is 5, this is 6. Okay. Now, what is the what is the resisting forces are developed in the what is the resisting force acting in all the bushes? Here, I mean, we know the force, right? P. I mean, this is a D is nothing but the bush is sitting on the pit circle diameter D, hence P into D by 2. P into D by 2 is nothing but our nothing but our equal to our torque transmitted. I mean, MT is equal to P into D by 2. Sorry, this is a transmitting torque. MT is equal to P into D by 2. But here we are using, how many bushes we are using? 6, mean number of bushes 6 and N is equal to 6. Okay. Now, now see the projected area. Now, as I told you that, what is the P here? We are putting P, the force exerted while the rotation of the shaft, the force exerted on the bush, right? What is the P? How can I find out the P? Just to see this projected area of the bush here. Okay. Now, in this projected area, I mean, this is the force acting. P is exerting this this surface area. This this projected area. Sorry. Okay. Then what is the projection? I mean, area of the projection of the bush is LB, length of the bush, and the diameter of the bush. Okay. Now, now, I mean, here when the shaft rotates, the pressure is, I mean, exerting in this, the pressure, the intensity of pressure between the flange and rubber bush, intensity of pressure between the flange and rubber bush, this region, intensity of pressure between the flange and rubber bush. I tell you, this region, intermediate, the intensity of pressure in between the flange and rubber bush, that's what we are taking this projected area of the bush here. Okay. Now, I mean, D into B, dB into LB, and pressure, permissible intensity of pressure, permissible intensity of pressure between the flange and bush. Okay. Now, this is P, substitute in this equation A. Finally, we are getting this, I mean, our transmitted torque transmitted on the in this coupling. Okay. Now, I mean, see, very important. See here, the permissible intensity of pressure in the rubber bush and I mean cast iron flange. Cast iron flange, we are usually considering 1 Newton per mm square as per the design data book. 1 Newton per mm square. I mean, in this situation, the ratio of the length of the bush and outer diameter we are considering equal to 1. This is nothing but effective diameter. This is also called effective diameter. Now substitute these relations L by B, D by ratio 1 and Pm is equal to 1 Newton per mm squared in this equation. In this torque transmitted equation, MT is equal to 1 by 2 Pm dB into LB into Dn. Then finally we are going to get this equation. Here dB is equal to, I mean, LB is equal to dB. Hence dB squared into D into N. Pm is 1 Newton per mm squared. Okay. Now this is our, when we are considering that effective diameter. Okay. Now, I mean, the outer diameter of the bush is up, I mean, anyway, from this relation, we know the torque, how much torque we are going to transmit. We know the number of bushes, how many bushes we are using in this mechanism, right? We know the pitch circle diameter. As per the empirical relation, we are able to find out. Then finally, from this relation, we are able to find out the diameter of the bush. Okay, diameter of the bush. Now I come to the fin. Now the fin is inserted through this hole. The fin is inserted through this hole. Now we didn't talk about the fin now. Now we are going to talk about the fin now. The fin is subjected to direct shear. Direct shear when the force P is exerting on the fin. Okay. Hence, we are using direct shear stress formula. Now, direct shear stress is equal to P divided by pi by 4 d square. Pi by 4 d square. Then, from this relation, we know what is P. P is nothing but dB into LB into PM. Substitute here. Finally, we are getting this equation. Tau is equal to 8 mt divided by pi d1 squared into d into n. Now, in this, we know the permissible shear stress of the fin material, and we know the how much amount of a torque to be transmitted, and we know the number of bushes, and we know this dimension capital D pitch circle diameter from the empirical relation. From this equation, we are able to find out what is d1, what is the fin diameter. We are able to find out. As per the Indian standard, we are considering the allowable shear stress of the fin mostly 35 Newton per mm square. 35 Newton per mm square for design limit. This is a permissible limit for the fin while designing the flexible flange coupling. Now we are going to just relook about these procedures, steps. What are the steps to be followed while designing the while determining the dimensions or designing the flexible flange coupling? Now this here, now this is a standard format. I mean, if you know the power, we able to find out if you know the power and the rotation speed of the coupling, we able to find out how much torque is transmitted. Once we know the torque, we able to find out the diameter of the shaft. Now I come to the dimensions of the flange. This is already we have been discussed just now. Based on the empirical relations, we able to find out the dimensions of the coupling. Okay. Now here also we are using, I mean, this is the coupling. I mean, what is this? This is like, looks like this is the hollow shaft. The hub is looks like hollow shaft. Hence, based on the hollow shaft, hence we would like to verify the stress limit. I mean, when the looks like hollow shaft, the tau is equal tau by j is equal g theta by L. I mean, T by j is equal g theta by L. I mean, from these relations, we already discussed this enough information. From these relations, we are able to find out what is the tau. This tau is within the permissible limit or not. I mean, this is actual tau of actual shear stress of the hub. Then this this permissible, this actual stress is within the permissible limit or not, we would like to verify while designing the, I mean, coupling. Because we have been used empirical relation. Whatever empirical relation we use, that DH is also empirical relations. That empirical relation, based on we defined the dimensions we are going to use here, then we are doing cross verification of this permissible stress value along with our actual stress value of the hub. Okay, now this is the this is the stress verification. Now I come to the flange junction. I mean, calculated. This is the, I mean, the junction is subjected to shear stress. Now see here, this junction, we are talking about this junction. This junction, this is the junction. What is this junction? If you take, this is the three-dimensional view. In this three-dimensional view, this is the T. Thickness is T, already given here. I mean, what is the diameter? DH. Then what is the area? This junction is subjected to, I mean, from this design data book, they suggested that this is junction subjected to shear. Then pi DH into T, area in subjected to shear, right? Shear. Now what is the torque? This torque, this resisting torque is equal to DH by 2. Sorry. Here DH by 2. This must be equal to our transmitted torque. Now, from these relations, we know DH value, we know T value, we know most of the values. I mean, only we are going to find out this tau is within the limit or not, within the safe limit or not. At the junction, the shear stress, the flange coupling is subjected to into shear stress is within the safe limit or not. That is our intention. Okay, now I mean this one. Okay, now I come to the diameter of fin. This is standard empirical relation, right? I mean, this is the fin diameter. How to find out the fin diameter? This is the. I mean, here we are doing cross verification of the shear stress component. Suppose we can do cross verification of through this way also. We can do the our diameter of the fin. Okay. Now later, now the dimensions of the bush. Dimension of the bush is nothing but whatever we discussed earlier. This formula, from this we can find out the dimension of the bush. Okay, I mean calculate the effective length. Effective length when we are considering LB is equal to DB. But in the problem we are going to find out the actual dB and dB. That is important because we never discussed about the lining. Because see here, this is the lining. Also we are providing the lining between the bush and the fin, hence we never talk about that. But actual condition we have to discuss during the problem. You can understand during the problem discussion, you can understand. Now finally we are going to consider the based on the shaft diameter, we are going to define the um, length of key dimensions. Once we define the key dimensions, we would like to verify the stresses induced in the keys are within safe limit or not. Okay. I think now shall we move to problem? Okay. See the problem. If it is required to design the boost pin type flexible coupling, connect the output shaft to an electric motor to the shaft of centrifugal pump. The motor delivers 20 kilowatt power and is at 720 rpm of the flange speed, okay, rotation speed, and I mean rpm, 720 rpm. The starting torque of the motor can be assumed to be 150 of the rated torque. Design the coupling can specify the dimensions of the components. Now, which torque we should use for design the coupling? Please, someone reflect. Here they have given 150 percentage of rated torque. I mean, while the starting condition. Can you give me example? Simple example. Why we should consider this component, or this component may not be required. Which one we should consider for designing our coupling? Either 20 kilowatt or 150 percentage of rated torque.
150% of rated torque.
Yes. Yeah. Any example? Thank you. Any example? Practical example. See.
Sir, motorbike, sir, when it is starting, sir.
Yeah, exactly. And is the same way if you consider train. At the initial condition, it will take enormous torque. Once running, even if you switch off the engine, then the train will move freely. That's what the initial torque is very important for the mechanical system. Okay. Hence, the rated torque 150 percentage should be used for our design purpose. Now, now first we see the selection of materials. This is a theory, just you go through that, you can get it, because we almost discussed most of the coupling. For example, I mean this design, this coupling I didn't tell you that. Now the flange coupling, flexible flange coupling made of cast iron carbon, I mean cast iron grade FG200. Fins are made of carbon steel. Okay. And similarly, the maximum allowable peripheral speed of the coupling, they are allowing 30 meter per second. Okay. And I mean, this kind of information we discussed every coupling. For sleeve coupling, the material is different. I mean, this clamp coupling, the material is different. And rigid rigid type coupling, rigid type flange coupling, the material is somewhat different. So based on the material property going to be varying. Okay, we already know know that information. So based on that, the justification, suppose the problem, whatever we are asking the problem, we are going to give the material properties straight away. You don't need to worry about this section of the material. See here how they are choosing. The shaft are subject to torsional shear now on the basis of strength and plain carbon. Here this is the soft material. Its yield strength is 380 Newton per mm square. 380 Newton per mm square. And factor of safety is to be considered in the shaft 2. The keys are subjected to shear and compresses. The fins are subjected to shear and bending. One more thing, see here, I would like to tell you here. Now, here the gap, we are maintaining the gap because the gap is, we are following in the flexible coupling. If you are based on this gap, based on this gap only, we are obtaining these benefits. Lateral misalignment, axial misalignment, angular misalignments can be obtained easily when we are allowing the gap between the input flange and output flange. Okay, now when we are using, now one more thing, this flexible coupling, I have to tell some more information, then only we can understand while discussing the problem. Okay, the torque transmitted by the force of passing through the bush in case of flexible coupling, because of here the permissible pressure, we already know that 1 Newton per mm squared we are considering as a standard value, right? Now the flexible coupling, here we are using either a greater number of bolt in that sense fins, and rigid coupling also larger bolt circle, the length of the bolts also it will be more. When the length of the bolt will be more, then it may cause us the bending effect. Hence we would like to do cross verification, our bending says how much bending says created in the fin within the permissible limit or not. That also we have to consider in our design process. Okay, design process. Now I come to the problem. Now now this is a keys. See here, this is the pins. The keys are subject to shear and compresses. Fins are subject to shear and bending. That's all. Fins are subject to shear and bending stresses. On the basis this, there's yield strength criteria 400 Newton per mm squared when we are considering grade 30 C8 for selected for keys and fins. See here the factor of safety for the key and fin is 2. Similarly, the compressive yield strength, we are assuming that 150% of the tensile yield strength. Compressive yield strength always higher than, here we are considering 150% of the tensile yield strength, not always higher. Based on our design approach, we have to consider. Okay, here we are considering 150% of yield strength, 1.5 times into 400. When we are finding the compressed yield strength. Okay, now the flange is complicated shape. Now the flange material is now gray cast iron. The ultimate strength of the flange. Is now 200 Newton per mm square. Okay. Now this is the justification, and the factor of safety is a 6. Factor of safety 6. And these parameters to be given to you. When we are asking the problem, these parameters briefly it will be given to you in the exam. Okay. Now first, based on this material justification, selection of material, the justification given for here for the selection of material, based on this given explanations, now we are defining the permissible stress value for shaft. For shaft, already first shaft is defined here. Shaft mean 0.5 times of 380 divided by 2. This is permissible stress for the shaft. Key is already given you. Key is already given here. Okay. I mean 200 Newton per mm square. Okay. So I mean 400 Newton per mm square divided by 2. I mean 100 Newton per mm square. Then crushing stress also given here. Now I mean 1.5 times into 400 divided by 2, 300 Newton per mm square. And the fins also, tau is also given. Tau is already, we know that as per the Indian standard, we know that 35 Newton per mm square, what we discussed in the early. Yes, here, what we discussed in the early. Okay. Now come to the flange. From this justification, we are finding this permissible stress value for the flange. Now go by step by step for the design the flexible flange coupling. The power is given. I mean, power is already given 20 kilowatt, but we are multiplying 1.5 because of rated torque is, I mean, starting torque is 1.5 times of the rated torque. Hence, based on that, we are finding the torque transmission capacity of the flange coupling. Once we know that, from this we are able to find out diameter of the shaft 16 mt divided by d cube. These are known formula. I mean, finally, this is the diameter of the shaft. Once we know the diameter of the shaft, go for use the empirical relations. Then find the hub diameter, the length of the hub. Okay, hub diameter is 60 mm. I mean, length of the hub is 45 mm. Also, length of the hub is 45 mm, and the pitch circle diameter is 120 mm, and thickness of the flange output flange thickness is 115 mm, and thickness of the protective rim is 8 mm. Okay. Now, once we know that hub diameter, I mean DH, and shaft diameter, hub is acting as a hollow shaft. Then now we have to do cross verification. As I told you earlier, tau is equal to mtr by j. From this relation j, we know this is hub diameter, this is a shaft diameter, these are known values. From this we are able to find out this stress value. This is actual stress induced in this junction while rotating the flange. That is 10.10 Newton per mm square. That is less than our permissible value. 16.67 Newton per mm square. So less than permissible value. Now the CSS. Now I come to this. Now we would like to find out the shear stress induced at the junction. Yeah, this is shear stress induced. This is shear stress induced in the hub. Sorry. This shear stress induced in the hub. Now this is shear stress induced in the junction. Shear stress induced in the junction. I mean this portion. Sorry, earlier I told that one. Please change it. This region. This is a hub. Now this is a region, junction region. Would like to find out the actual shear stress. Now, I mean, see here 2 mt divided by dh squared t. I mean, dh we know, because these are the things we are obtaining from empirical relation, the dh value. Hence, we would like to verify the stress limit. I mean, actual stress induced in the junction. Then this is a 4.69 Newton per mm squared. Then this is the less than our permissible limit. This is with respect to hollow shaft design. This is with respect to the junction of the hub. Okay, junction of the hub and flange. Okay, now this is the 4.69 Newton per mm squared, which is less than our permissible limit. Now come to the diameter of the fin. Number of bushes are 6. Okay, now this is from the empirical relation 7 mm. Right. Now this is the fin diameter. Now fin diameter based on the empirical relation. Now the fin is, especially in flexible flange coupling, we would like to use the bending stress also to design our flange coupling components. Okay, now later we are going to apply later step, we are going to discuss the bending effect. Based on bending stress, we are going to define the fin size. Suppose the fin size, okay, I will come to you later. Now, before entering that, now we see the, I mean, see this permissible stress value in the fin. Now this is the equation. Tau is equal to 8 mt divided by pi d1 square dn. Now we know the d1, we know the 180, 120, I mean pitch circle diameter, this number of fins, finally 28.72 Newton per mm square. This is the actual stress induced in the fin. Then the actual stress is, I mean, less than our 35 Newton per mm square. Okay. Now I come to the dimensions of the bushes. Dimensions of the bushes. Now, I mean, this is also we discussed now earlier. 2 dimensions of the bush is equal to 2 mt divided by dn. I mean, already we discussed. I mean, this formula also where we discuss. Just I show you here. From this relation, 2 mt divided by dn is equal to db square. This is now from these relations we are able to find out the diameter of the bush and length of the bush. I mean, this is nothing but the effective diameter of the bush. Actual diameter of the bush we are going to discuss now. Okay, now come to the bending stress induced in the fins. What is the bending stress induced in the fin? Now, right? Now, this is the load we know already we discussed. P into, I mean, how much force exerted from the shaft to bush, and this is number of bulls. We already discussed this now, right? From this, we are able to find out what is the force exerted on the bush. On the bush, I mean, on the bush, I mean, on the pin through bush. Okay. 1105 Newton force is exerted on the pin through bush. Okay, now see here. Now, I mean, we have been seen. We can see here separately that out means schematic diagram here. This is the bush. This is the liner, brass liner. This is a bush. This is a flange, driving flange. This is the output flange, driven flange. Now, as per the effective length calculation, this is a 35 mm. This length is, as I told you, that this gap is required for managing our misalignment 5 mm. This gap. Now, this total length is 40 mm. Right. Now, what is the bending stress induced here? What is the bending moment induced here? Bending moment. I mean, this is the bending moment. What is the bending moment induced here? Now, P into, I mean, whatever the forces are acting in the left hand side flange, driving flange P, see here, P, this force, P, right? Now, then the outside, I mean, output flange, it's a driven flange. The force must be opposite, but in same amount of force should be exerted on the fin, then only the system will be mechanical equilibrium. Hence, now what is the length? Here, this is P into, I mean, this is a P into the force exerted here, P plus, I mean, P into 5, the gap 5 mm. I mean, this is uniformly distributed load, hence I am introducing 35 by 2. Okay, 35 by 2. Finally, we are able to get this is a bending moment acting in the fin. This is a bending moment acting in the fin. Now, this is a bending moment acting in the fin. Now, once we know the bending moment, we are able to find out the bending stress. Bending stress induced in the fin. Now, substitute here. I mean, sigma B is equal to 32 MB divided by D1 cube. This is the bending stress. Very simple concept. Sigma B by Y is equal to M by I. From that relations, because the fin is solid, I mean, solid diameter, solid, not hollow, soft, solid is soft. Hence, 32 MB divided by D1 cube. Now, the sigma B is already given to us. Okay, 200 Newton per mm square. Now, I mean, see here. I mean, numerator bending moment we know. Now, we would like to find out what is a D1. D1 with respect to bending stress. The bending stress is given here. Okay. Now, when we are finding the D1 here, the D1 is, 12 mm. You can take 11 mm also, doesn't matter. They might have been gone to, standard dimensions of the table. 11.10.82 mm means you can consider, as per the table, we can consider 12 mm. Okay. Now, this is a fin diameter, 12 mm. Now our fin diameter is 12 mm, not 7 mm. Suppose here, earlier we have found this fin diameter 7 mm. Now, if you 7 mm, if you consider in your design, then your fin is unable to withstand the bending stress. Unable to withstand the bending stress. Hence, we have to consider 12 mm. Now, if you consider 12 mm fin diameter, substitute value here, the 12 here. Still, your shear stress in the fin is less than the 28.72. When you put to 12 instead of 7, you put to 12, your stress value is less than this. Then, as compared to, for example, maybe a 20 Newton per mm square. For example, sorry, I'm not telling exact value. When you put a 12 mm square, right? Then this value now still less than the or permissible limit. Even better. Okay, when we are going for more diameter of the fin. So this way we have to compare. We have to compare the design. When we are designing the fin dimension based on the shear stress as well as bending stress. You may expect this kind of question in the objective type. Okay. Now that's what we are considering. Fin diameter is now 12 mm. Now come to this actual condition of the design. Now the fin diameter is 12 mm. What is the enlarged diameter? Now we are talking about this only. Now we are talking about this dimension. Actually, this enlarged diameter, hence the enlarged diameter we are considering 12 plus 6 mm. This direction, upward direction the 6 mm, the downward direction 6 mm. Okay, then 12 plus 6 going to be 18 mm. 18 mm. The fin diameter at the enlarged end. Here is 12 mm. Here is 12 mm. The length is we know 40 mm. 35 plus 5, 40 mm. Now I come to this bush dimensions, axial bush dimension. Now see here. The inner diameter of the bush is 12 plus 4 mm. 12 plus 4 mm or 12 plus 4 mm is 22 mm. Why 12 plus 4 mm here? Here we are using bush. Sorry, we are using a line. Brass lining. Depends on lining. The data might have been given from the data book, might have been taken from the data book. Here we are using the lining here 2 mm, then the top lining 2 mm, the bottom lining 2 mm. Then actual design of the bush now this is 22 mm. Inner diameter of the bush is 22 mm. Okay, inner diameter of the bush is 22 mm. But actual thickness of the bush, as per the standard data book, 10 mm, 22 plus 10 plus 10. Here, this side is 10 mm, this side is 10 mm. Thickness of the bush, then finally 42 mm diameter. The bush diameter is 42 mm. That's what we are using, 42 mm diameter of the bush. Okay. Now the bush diameter is 42 mm. Now I come to this later, the dimensions of the key. We already know the dimensions of the key. Now the 30 mm diameter, and here this is the flat key 8 into 7 mm. 8 into 7 mm. Here the length of the key is a 45 mm. This is a diameter, 30 mm diameter. For 30 mm diameter of the shaft, we are using 8 into 7 dimensions of the flat key. The length of the key is 45 mm now, right? I mean, we already know that this is a tau shear stress. This is the crushing stress. Based on this, we able to find out this. I mean, actual stress value. Actual stress value. Okay. Now, I think this is. I think verify this stress value later. I forgot to. There's something wrong. Okay. And the last one is crushing stress value 168.42 Newton per mm squared. That is also less than the our permissible value. Less than our permissible value. So now we have completed this. Now we have to draw the diagram. I mean, in the exam, we may ask to draw the diagram. You have to practice such a way that to draw the diagram. You don't need to draw three-dimensional view in complicated dimensions. I mean, here we are mostly concentrating the bush dimensions and fin dimensions and outer diameter of the flange and hub diameter. This way you have to reflect in your answer. Okay. So now universal coupling, this is just you go through this. I have attached the slides here. Wherever the intersecting shock, we are using universal coupling. Very simple. Now this is very simple, and here also there's a procedures also same. I mean, this is the equations are given. I mean, torque, where the torque transmitted by shaft, the torque transmitted double shear on the fin, double shear on the fin. Okay, this is very simple. Anyway, one we are going to cover that whatever we discussed, clamp coupling, sleeve coupling, and rigid flange coupling and flexible coupling. That only will be covered in the your syllabus and in your exam also. Okay, this is for your understanding. I put it universal coupling. This is all-them coupling. Now wherever this shafts are, I mean offsetted distance, but both shafts are in parallel. Then during power transmission, all-them couplings are using here for the lateral misalignment. This kind of coupling is very useful. Okay, just go through this point very simple manner. I have written here. You can easily understand. This is the summary of this chapter. What are the formulas we discussed as of now? Some of the things I didn't cover here because I mean the rigid flange coupling and the flexible flange coupling formulas I didn't cover. Anyway, just now we discussed. Go through that. Okay, if you have any doubt in this problem or any doubt in this chapter, please go ahead. Now we start the next chapter. At least we have to start the topic. Any doubt? How many students are there?
Oh, sir.
76. Okay. I do one thing. Now I just a minute. Okay. We continue, no problem. Okay, come to this gears. What is the gears? What is the gear? You might have been studied in the basic mechanical engineering subject in your first year subject, right? What is the gear? Yeah, please reflect. Just a brief conclusion about the first chapter. In the first chapter, we discussed the keys. Sorry, we started solid shaft design. Then we came to hollow shaft design. Then we discussed about keys, different types of keys and design of keys. And the hollow shaft and solid shaft at a different load condition, torsion load condition, bending load condition, tensile load condition. I mean, there are three ways we discussed. One is based on strength. The second one is lateral rigidity, bending, torsion, and combined effect. We discussed the design of the shaft, both hollow and solid shaft, and later we discussed the keys, different types of keys. Especially we discussed a flat key and square key and splines, and also Kennedy keys design we discussed. Later we discussed about these couplings, different types of couplings. Okay. Now we move to the gears. Now please reflect your answer. What is a gear? Because you are, I know that you are know this, you know about the gear, but I'm expecting your explanation, brief explanation.
Sir, a disk which contains the peaks which act as a fulcrum for transmitting the power.
Exactly. It is act as a transmitting the power from one unit to another unit, right? Now, so that's what now the gears. I mean, anyway, first we see these gears. Gears mainly used for transmission of the power and motion from one shaft to another shaft. And we are going to discuss some type of gears in later. There are two basics, base. We are going to consider two different methods of failure. You see here, there are two basic modes of gear tooth failure, right? I mean, breakage of the gear due to static and dynamic loads. First case. Second case, I mean, surface destruction. I mean, surface dissection. I mean, see here, this is the surface, right? Surface destruction. Now, I mean, there are two ways we are going to discuss very detailed manner of the gear design. One is bending, another one is due to fitting effect. One is due to gear tooth due to bending effect, and the second one is gear tooth due to pitting effect. We will discuss what is a fitting. I will tell you later. Okay, just keep in mind now. In order to avoid the failure of the gear tooth due to the bending effect, I mean, SB greater than the effect of effective load, P effective load. Now, the SB is nothing but beam strength. Beam strength. I mean, the maximum tangential force, PT. Where is the maximum tangential force? This is the maximum tangential force in PT. PT, right? Maximum tangential PT that the tooth can transmit without bending. Without bending failure is known as beam strength. How can I say here bending strength? See here. Now, I mean, this looks like simply a cantilever beam concept, right? The beam. Now the one end of the teeth is fixed. The other end is load is acting, right? This is nothing but our beam length. For H is now this is nothing but if I turn to 90-degree, that is height of the gear, height of the teeth. Sorry, height of the teeth. Now, in this case, this is looks like this is the load is acting here, right? Now, this is the load is acting here. Right? This is L. This is L in when we considered cantilever beam. Now here we are consider the beam teeth height. Teeth height. This is width of the teeth. This is the thickness of the teeth. Okay. We are going to discuss the terminology, gears terminology in later. Now, I mean, based on this effect, we are going to study that is called beam strength. Beam strength. The second important thing, in order to avoid the breakage of the gear tooth due to pitting. Pitting, I will tell you later. We are going to discuss later. Okay. I mean, anyway, pitting. I mean, pitting where the wear strength. Wear strength means nothing but SW must be greater than the effective load. Our design wear strength must be greater than the effective load. The maximum tangential force PT that the tooth can transmit without fitting failure, known as wear strength, is known as wear strength, is also called Buckingham equation. This is very, very important. These two concepts, Lewis equation and Buckingham equation. You can expect any objective questions from this. Okay. Now this is now not only this, based on contact stress also. Now the contact stress. Now, I mean, see for example, now without these two wheels, I mean, I'm not considering any teeth here. Just I'm taking this is a pinion, right? This is the pinion wheel. This is a gear wheel. Without now the contact stresses are greater than the surface endurance strength. When this contact stress in this region are greater than our surface endurance limit, surface endurance strength. Anyway, in the last semester you studied, we discussed also endurance limit stress. When the contact stress are greater than the endurance stress, that also causes the failure in the gear. Now, these are the things, these two things are very important. We are going to discuss in later in detailed manner. Okay. Now, I come to this. Now, this is what type of gear this? Have a spur gear. This is the bigger wheel is big one is gear. The cycle, this one is a pinion. Pinion. This is gear. Okay. Now I come to this. As I told you that what is a gear, someone reflected a very good answer. Now we go through some of the basic explanation, then we enter into this deeply in the design of gears. Okay. Now
The time up, sir.
what?
It's 11 a.m., sir.
Okay, thank you. Okay, I stop here. And this week I may take one extra class. Please give me a slot. Kalyan?
Yes, sir. I will arrange.
Yes. When is our CR meeting?
Around February, sir. In February.
Okay. Okay, please go ahead if you have any doubt.
No doubt, sir.
Okay, guys, thank you. Kalyan, share me the attendance, okay?
Yes, sir.
Thank you, sir.
Thank you,
sir.
Amarnath. Thank you, guys.
Thank you, sir.